Hi everyone, welcome to this webinar today where we're going to talk about why our road safety programs not achieving the expected reduction in DSIs that we're wanting. Really, the key objective is to try and achieve better network road safety outcomes from our programs. So the problem, regular road safety program evaluations in Victoria, Australia and some in New Zealand have shown that road safety programs are not achieving the safety benefits forecasted in the project evaluations. This is also occurring in other countries. Blair Turner, while working at the World Bank, confirmed that this occurs in many programs in many countries. The impact of this is that we're getting fewer deaths and serious injuries saved at treated sites and often lower network-wide benefits of our road safety investment. It is very important that we are realistic about what can be achieved through our programs. This webinar will look at the three main reasons why our road safety programs are not delivering the savings in deaths and serious injuries we are predicting and how we can improve the accuracy of these predictions. And just going straight into what are the three reasons for that I think these programs are having reduced effectiveness. So the first two are at a site level. So often we're using overinflated crash reduction factors, CRFs, to estimate safety benefits. And this is because these CRFs have been based on studies that are not adequately taking into account issues such as regression to the mean, which I'll talk a wee bit more about soon, and include additional benefits associated with multiple treatments. So sometimes we have a reduction that's for a particular treatment, but it also includes benefits from other treatments that were applied at the same time. There's also a reduction in safety benefits at many locations because of design compromises. We're not able to have a fully continuous shoulder barrier and median barrier because of intersections and access points. And many of the CRFs we have are based on those ideal road designs that we have on expressways and motorways rather than normal rural highways, for example. This often leads to these design compromises, just the issues with the road, and are we adequately reducing the safety benefits as a result of those particular changes. For example, actually having gaps in the median for intersections may actually increase some crash types like U-turning crashes if they're occurring in these gaps without suitable design. And the third issue really is more at a network level, in that CRFs are applied to overinflated crash numbers. So most of the sites that we identify for treatment have higher than normal recent crash history, and we know that due to regression to the mean, the crashes will go down at those sites anyway. So while we might claim quite big reductions at those locations, they may actually overestimate the contribution that the treatment of that site makes to the overall network crash reduction, because we haven't adequately dealt with regression to the mean. So I think it's good to reflect on the fact that crashes are very random events, particularly the more severe, fatal and serious injury crashes. And so we know from some work that was done by Dr. Fergus Tate that in New Zealand over 60% of fatal crashes occur at sites which had not had a fatal or a serious injury crash in the 5 years previously. You can see that on the right-hand graphs. Other than in cities where we have some quite major intersections where we do get repeat crashes occurring, but across the network, a lot of our fatal crash sites appear like lightning bolts at sites that we haven't in the past necessarily seen a problem in terms of crashes. And we have this issue called regression to the mean that occurs. So this is some simulated data at a site of crashes that have occurred over a 25-year period. And you can see how the crash rate jumps up and down because of the random nature of crashes. And even if you take a 5-year average, that first 5-year period is quite a lot higher than the second 5-year period, and the mean, which is about 4.23 crashes per period across this time, is somewhere in the middle. So often the sites we're treating are these high crash sites, and they will regress down anyway in the subsequent 5-year period because of regression to the mean. And so we are sometimes overestimating the benefits of crash reduction measures, treatments, because we are only looking at sites which have high crash rates when we assess the benefit of treatments, and often we are applying a reduction that's unrealistic. This is a bit of an example showing the regression to mean effect at these 4 roads, A through to D. The actual underlying crash risk at these sites based on a crash prediction model is 3 fatal or serious crashes in a 5-year period, which is shown by the 3rd column. But what we actually observe at these sites that we pick for treatment is usually a crash rate above that typical rate. And so you can see that 3 of the 4 sites have a crash rate well above 3, or one has one at 3. We know from the research that you'll get a reduction from around 3 to 2 crashes at these sites by applying a treatment. So the effective reduction is from 12 down to 8 if we used underlying crash rates. But if we used the observed crash rates, the apparent reduction is from 18 down to 8, which is a 10 crash reduction. But we're saying 6 of this in this case, 6 of that crash reduction is actually due to regression to the mean. Only 4, a reduction in 4 serious and fatal crashes is associated with the treatment. Now, if we use this type of data without correcting for regression to the mean in analysis, we would estimate that we get a 56% reduction in crashes from 18 down to 10, and compared to the actual reduction of 33% from 3 down to 2. So you can see how not correcting for regression to the mean can cause problems in terms of the number of the benefits of treatments. So just looking at those 2 of those problems, problem 1 and problem 3. In the first case, we have crash reduction factors that don't take the regression to the mean if they're not being developed correctly. You can see that would apply to the underlying crash rate 12, 56%. So we'd assume you get a 7 fewer crashes, when in reality we should be applying 33% to the 12 and estimating 4 less crashes. In the second case, inflated crash benefit quality reduction factors are applied to the observed bias crashes. You can see if we apply it to the 18 crashes rather than the 12, which is a better reflection of the underlying crash rate and what we see going forward, even with a 33% reduction, so we've got the correct crash reduction factor in this case, we'll overestimate the benefit. Instead of 4 fewer crashes, we'll end up with 6 fewer crashes if we base it on the actual crash history, not the underlying crash rate. So this example illustrates 2 of the problems that we've been talking about. Now, one of the issues that we have in safety investigation is we are to focus on the historic crash rate at flare-up sites, and we go around chasing these high crash sites. It's a bit like whack-a-mole, that we're knocking those sites down and we think we're getting an effective outcome, but of course crashes, fatal and serious crashes, we know will flare up at other sites. So while we might have less moles poking up, we will still have them occurring in other locations, and we should not just be focused on those sites where we've seen a high crash rate in the most recent past. We need to focus on addressing the underlying crash risks to achieve network effects. And the best way to do that is to use some type of modelling method to try and understand whether the observed crashes at the site is realistic for that site, or we're seeing an overinflated number of crashes because of regression to the mean. Because overall, we want to reduce total TSIs across the network, not just at each individual site. We want to see the fatalities and the serious crashes coming down, and ideally to zero eventually across the network. Now, going back to problem 2, which is the correct use of crash reduction factors. The table on the left is from the crash estimation compendium, which is where all our crash prediction models and crash modifying factors, crash reduction factors, are kept in New Zealand. And we have these reductions for putting in wire rope for median barrier and shoulder barrier, and really those reductions do apply to sections of the network where we can have continuous median and shoulders, such as Q2 Drive here in Christchurch and the Kapiti Expressway up in Wellington, where there aren't accesses and intersections through that section that require you to have a gap in the median or install a major intersection. But in reality, what we do have is locations where we do have gaps in the median, and we, for various reasons, don't put in a roundabout or some other form of control. And therefore, if we assume that we're going to get continuous benefits from a median barrier through here, we haven't really identified that there will be a reduction in the benefit and the applied crash reduction factor because of the gap in the median, and vehicles could lose control and go through that median and have a head-on crash. And does the crash risk increase at the intersection, potentially associated with the fact that we've got a median now? And will people be U-turning through that gap? Now, in this case, the facility has been designed to allow U-turns, but in a lot of cases, it hasn't. So ideally, at all these locations, we have roundabouts, but it's not always practical to do that. And where possible, we don't have gaps in the median, and we use roundabouts or U-turn slots to aid people to access side roads and access ways. But that's not always possible, as in the case here, which is Stowaway 22, road to Pukekohe in Auckland, where there are a lot of access points. And you can see from the bottom right photo, obviously the median barrier can't be continuous because you've got intersections, access points through here, which make it very difficult to have a continuous shoulder barrier and also continuous median barrier. And we do need to have crash reduction factors or ways of adjusting the crash reduction factors to take this into account. So in terms of developing accurate crash reduction factors, it's really important that we use quality before and after studies. So what we're trying to do in these before and after studies is look at the number of crashes, that would have occurred at the site had the treatment not been applied, and subtract from that the number of crashes we did observe at the site. And ideally, you have at least 50 sites that you do that assessment at, and then often there is that complication that you may have a mixture of treatments being applied at a site, so that your reduction observed through the analysis may not actually be just because of a particular treatment. It's probably going to be overestimated above the treatments are applied, and they have their own benefits. So the basic needs in terms of doing the studies is what would have been the safety of the treatment in the after period had treatment been applied, and we need to know obviously from the crash record and have enough years of data what the safety effect was in the after period. Now, in a naive study, we just used the crash period in the before case to represent what would have occurred at the site in the after case. But of course, that maybe what happens in the after case is influenced by an increase in traffic volumes or bike volumes, and this regression to mean effect likely will have occurred in the after period. And so some of that reduction that you'll see if you just use the before data as an estimate on the after data will be due to regression to the mean if you're looking at high crash sites. So we do have this selection biased, where we do have these high crash sites that generally got crash rates much higher than what we would expect at these sites, and so we do have that regression to mean effect. And these things happen at maybe intersection black spots and at level crossings, where fatal crashes are quite rare. So the sites where they are occurring, that crash may not reoccur every 5 years for the next 25 years. It might just be a 1 in 50 year event. So it follows that the count of crashes in the before period is not a sensible base estimate of the expected crash count in the after, due to regression to mean and changes in traffic volume and bicycle volume in the after period. So what is? Well, the way we do it is we take both the observed in the before case, and we also use what we'd expect in the after case based on similar sites. We're using a crash prediction model or safety performance function, combining those two bits of information together to estimate what what the number of crashes might have been in the after case had the treatment not been applied. And this is kind of shown in this graph where we have the observed crash rate up the top, which is high because of the regression to the mean effect and that bias by selection in terms of the sites we treat, and then the prediction from the model. And we use a weighted average of both to take into account some of the regression to the mean. Now, why don't we just use the predicted frequency? Well, there may be factors at that site that are reflected in the crash history, and therefore the crash rate may be higher at that site, the underlying crash rate, than the all the other sites that have that similar volume and characteristics. So we do acknowledge that some of the increased crash risk that you observed to be above what you predict or would expect may be due to site factors. But we are taking into account regression to the mean, and considerable research has shown that this approach does improve the accuracy of the crash reduction factors that you will develop for use in appraisal of road safety programs. So it's really important that the studies had done this adjustment, and the empirical Bayes method, which is this weighting method, is the way to go. So I'm just going to go through one example here of what can happen if you don't take into account regression to the mean, and how you can be off in terms of your estimates of the what the crash reduction factor will be. So this is based on some research in the North America, and in this case they were looking at the true benefits of installing barrier arms at rail crossings with flashes. And of course they identified a lot of sites where they had actually had fatal and serious crashes, so there was that bias by selection. So in the before case they had 286 crashes fatal and serious crashes at all these sites. And then they observed at these sites in the after period only 114 crashes. So the apparent saving is 172 crashes, or a 60% reduction, so a big reduction. But in reality, when you use the empirical Bayes method, the crashes expected in the after case had the barrier arms not gone in was more like 208 crashes. Take into account that some of those sites, the crashes that were observed were unlikely to reoccur in the after period. It was because of regression to the mean that the number of crashes at some sites was higher than expected. So the actual savings were more like 94, which is quite a lot less than the 172 that would have been estimated using the naive study of taking the before crashes as a representation of what would have occurred if the treatment hadn't been applied in the after case. So the reduction was more like 45%. And you can see that's quite a big difference. And if you use the 60% at your other sites that you're treating, you'll end up overestimating the benefit. And then when you come back to evaluate those sites, you'll find generally that the reduction wasn't as high as you expect. Just returning back to problem 3 and needing to carefully apply crash reduction factors. So what I'm saying here is that at this site, the stat I-22, there are all these access points and intersections through here, which means that we won't have continuous barrier through this section of road unless a new road is built to service all these properties, which is probably unlikely on most rural highways. So we do really need to have a method and some crash reduction factors that can be used in this situation to estimate the reduced number of crashes. Because I suspect what happens at the moment is the benefit is reduced in proportion to the amount of barrier that's not actually applied, but there are issues like U-turning that may occur in these gaps in the median, which may actually increase the crash rate. So we do need to look at how effective putting in shoulder barrier and median barriers with an intention to make it as continuous as possible is on these types of highways, and identify any issues, safety problems that are caused by leaving these gaps in the median. So thank you for listening, and I'll take questions now. Unfortunately, because I had to record this, again, because it didn't record in the first case. I haven't actually managed to capture the questions that were discussed in the initial webinar, but hopefully the repeat of the presentation will be useful in terms of any safety programs that you want to develop in the future. Thank you. Bye.